Welcome to all of our 11th students. Today we are going to see equations of uniformly accelerated motion by calculus method in our kinematics lesson. Already we know about displacement, velocity and acceleration. What is the definition for displacement is nothing but shortest distance between initial and final position. Then we have definition for velocity. Rate of change of a displacement is nothing but velocity. Like that we have a acceleration. Definition for general acceleration definition. Rate of change of velocity is nothing but acceleration. Anyhow, here we are going to see the object in motion with a constant acceleration. Constant acceleration means particle moves in a definite direction with a change in velocity with respect to time remains constant. Then only acceleration remains constant, or otherwise we can call the uniform acceleration. So for that we will take one example diagram. Suppose one object is start to move. O object we may mention that maybe moves in a straight line. But we are going to see about that uniformly accelerated. That's why we made the object to move in a uniform acceleration. Anyhow, it moves from this position to some other positions. If the object starts to move, means there we have displacement with respect to time. At the time of making a displacement, there we have a velocity for object. It may be changes with respect to time. Then only we have a acceleration. If any particle has a displacement and that displacement is changes with respect to time, there we can say we have a velocity for the particle. If the velocity changes with respect to time, then we can say that we have an acceleration, even though here uniform acceleration. Uniform acceleration means change in velocity with respect to time remains constant. Anyhow, it may be moves in a certain straight line path. There we are going to tackle here 2 points. I may mention as a and B. This may called as a initial position. It is continuously moving, but it is taken as a initial position. At this point, time of moving may be taken as t is equal to 0. There, because of its motion, we have velocity for the object, u velocity. And it moves from A to B. At the time of reaching the point B, it will take certain time. So that's why t is equal to t. Time to moving from A to B can be taken as a t. Because of that acceleration, the velocity not remains constant, it is changes. That's why this position velocity may be taken as a v velocity. Because of the change in velocity with respect to time, there we have a acceleration. There we have a displacement. The shortest distance between these 2 points may called as a displacement, that is going to represent as a s. So what are the notation we'll going to use for the factors we are going to mention? S is nothing but displacement. Next, u initial velocity. Okay. And next V, small v, may refers to further final velocity. What is that? Final velocity. And here A, acceleration. But what type of acceleration we are going to use means constant acceleration. And we have independent factor, time, may represent as t. These all factors going to relate and gives the equations of the motion. But for the deriving the equations of the motion, that acceleration should be taken as a constant acceleration. Constant acceleration. So that's why we are mentioning constant acceleration, otherwise called as a uniform acceleration. So for that, according to our definition, we will given that velocity and the time relation. Velocity time relation is nothing but first derivative of velocity is nothing but acceleration, but it should be with respect to time. So that's why we are going to take a heading velocity time relation. Velocity time relation. Velocity changes with respect to time can be defined as first derivative of velocity with respect to time, that may called as a acceleration. So that's why acceleration can be taken as first derivative of velocity with respect to time. That's why dv by dt, A is equal to dv by dt. dv is nothing but a change in velocity. So that's why we have initial and final velocity. That will be taken at some certain time. That's why if velocity is u at t is equal to 0, then if velocity v, this is u is nothing but the initial velocity, v is the final velocity at time can be taken as a t. That's why we have a limitation in velocities from u velocity to v velocity. At the same manner, the time may be taken as 0 time to t time. This is going to used in our calculus equations. Is a differential calculus. We are going to relate that initial and the final velocity using the integral calculus. So that's why here we are going to change this equation as a dv equal to a into dt. So totally you want to find, there we are using a integration. A finite integral we are going to use. Finite integral means we have a limitation, lower limit and upper limit. So for that u and v, that is the initial velocity and the final velocity. There the time is 0 to t. We know that acceleration remains constant. That's why that constant should be taken out in the right side of our equation. Anyhow, if it integrated, we will get v. There we have a lower limit and upper limit, u and small v equal to a into integral 0 to t dt. Now we are going to substitute that upper and lower limit. First we are going to substitute the upper limit v for this v. This v is going to substitute for this v, that is the upper limit v minus, for this lower limit is u equal to a into integral dt can be taken as a t There also limitation 0 to t. If you substitute it, v minus u equal to a of t minus 0. So for rearranging the equation, v minus u is equal to at. Otherwise, finally, v is equal to u plus at. This is the first equations of the motion. By calculus method we are deriving. By the calculus method. Any other method we have means, we have a graphical method also. That is in our lower sections. But we are here, we are using a calculus method. Differential calculus and integral calculus we are going to use. So the first equation, this is the first equation. Based on that velocity time relation, the first derivative of velocity with respect to time is called as acceleration. That equation is going to rearrange and makes integration. Finally, we will get that v is equal to u plus at. V is equal to u plus at. This is the first equations of a motion with a constant acceleration. Next, we are going to see displacement. Second one is a displacement time relation. Okay, anyway. So, displacement may be changes with respect to time. It is nothing but change in displacement with respect to time is called as a velocity. Here, we are going to use the calculus method. That's why, first derivative of displacement with respect to time, that may be called as a velocity. That's why simply small v is equal to ds by dt. ds by dt. Now we are going to derive that displacement equation. That's why we are rearranging this. ds is equal to v into dt. Okay. Already we know that v is equal to u plus at. Already we know that v is equal to u plus at. That value is going to substitute in our equation. That's why ds is equal to, instead of v, we are going to substitute u plus at. u plus at into dt. Then that dt is going to taken in for both the factors. We will get ds is equal to u dt plus at into dt. Suppose the particle is at initial position. Particle is at initial position. There at initially displacement value s is equal to 0. There the time of can be taken as t is equal to 0. Okay. If the particle is moved certain distance for our final position, finally displacement value can be taken as s at the t time. So that's why limitation for that displacement is 0 to s, time limitation is 0 to t. So we are going to derive the expression for the displacement. We are making the integration, this equation. So integral ds equal to integral u dt plus integral at dt. Here we want to substitute the limitations. The displacement limitation is 0 to s. Time limitation is 0 to t. Very simple. Here also we are substituting 0 to t. So we are differentiating with the integration. Integration and differentiation cancel. Yes, there we have a limitation 0 to s is equal to. Here time is going to integrated. That's why u into t. Their limitation 0 to t plus is a is constant out integral 0 to t dt. If we substitute it, we will get s is equal to, here also u, then t minus 0 can be taken as a t, ut plus, if integrated as a integral t dt, we have the formula integral x to the power n into dx. So if we substitute it, we will get x to the power n plus 1 divided by n plus 1. So like that we are going to use. For that we will get that is a t squared by 2. The limitation is 0 to t. Then if you substitute, you will get s is equal to ut plus of a. First upper limitation we are going to substitute, that is nothing but t, that's why t square itself. Then lower limitation is 0. If you substitute that lower limitation, that becomes a 0 itself, that's why s is equal to ut plus of at squared. This is the second equation of the motion. It is called as a displacement equation. This equation is called as a displacement equation. Already we have derived the relation between initial, final velocities with acceleration and time. First equation, d is equal to u plus at. Second equation is a displacement equation, s is equal to ut plus of at square. Anyway, next we are going to see in that velocity displacement relation. Okay. Here we are going to take an acceleration equation. The first derivative of velocity with respect to time is called as acceleration. A is equal to dv by dt. Instead of that velocity displacement relation, the displacement is going to be included in that right side. That's why multiplied by ds divided by ds. So here we are rearranging that dv by ds into ds by dt. We know that ds by dt is nothing but first derivative of displacement with respect to time, that is nothing but a velocity. So we can take an a is equal to v dv by ds. So I want to rearrange this equation. Rearrange the equation, that will take an a ds equal to v into dv. A ds is equal to v into dv. Here for displacement limitation is 0 to s, velocity limitation is u to v. That's why we are integrate on both sides. The displacement limitation is 0 to s, velocity limitation is u to v. We know that acceleration is constant, taken out a integral 0 to s ds equal to integral v dv can be taken the formula as integral x to the power n x to the power n dx. That's value is x to the power n plus 1 divided by n plus 1. So like that, if you take an v square divided by 2, limitation is u to v. So next, the left side we are going to simplify. A into integration differentiation cancel and s only. There we have a limitation also, s to 0. That's why as is equal to 1 by 2 or upper limitation is v. That's why v square. Lower limitation is u. That's why v square minus u square. Then if you take an 2 here, 2as equal to v square minus u square. Then we will take an rearrange the equation. V square is equal to u square plus 2as. This is the third equations of the motion. We are derived the third equations of the motion by using a calculus method. So first equation is v is equal to u plus at. Second equation is s is equal to ut plus of at square. Third equation is v square equal to u square plus 2as. Another one also we have, by using a initial and a final velocity, we will give the displacement also. So we will see next is a relation of displacement with initial and final velocity. Okay. Lower limitation that becomes a 0 itself. That's why S is equal to ut plus of at squared. This is the second equation of the motion. It is called as a displacement equation. This equation is called as a displacement equation. Already we have derived the relation between initial, final velocities with acceleration and time. First equation, d is equal to u plus at. Second equation is a displacement equation. S is equal to ut plus of at squared. Anyway, next we are going to see in that velocity displacement relation. Okay. Here we are going to take an acceleration equation. The first derivative of velocity with respect to time is called as acceleration. A is equal to dv by dt. Instead of that velocity displacement relation, the displacement is going to be included in that right side. That's why multiplied by ds divided by ds. So here we are rearranging that dv by ds into ds by dt. We know that ds by dt is nothing but first derivative of displacement with respect to time. That is nothing but a velocity. So we can take an a is equal to v dv by ds. So I want to rearrange this equation. Rearrange the equation that will take an a ds equal to v into dv. A ds is equal to v into dv. Here for displacement limitation is 0 to s. Velocity limitation is u to v. That's why we are integrate on both sides. There displacement limitation is 0 to s. Velocity limitation is u to v. We know that acceleration is constant. Taken out a integral 0 to s ds equal to integral v dv can be taken the formula as integral x to the power n x to the power n dx. That's value is x to the power n plus 1 divided by n plus 1. So like that, if you take an v square divided by 2, limitation is u to v. So next, the left side we are going to simplify. A into integration differentiation cancel and s only. There we have a limitation also, s to 0. That's why as is equal to 1 by 2 or upper limitation is v. That's why v square. Lower limitation is u. That's why v square minus u square. Then if you take an 2 here, 2as equal to v square minus u square. Then we will take an rearrange the equation. V square is equal to u square plus 2as. This is the third equations of the motion. We are derive the third equations of the motion by using a calculus method. So first equation is v is equal to u plus at. Second equation is s is equal to ut plus of at square. Third equation is v square equal to u square plus 2as. Another one also we have, by using a initial and a final velocity, we will give the displacement also. So we will see. And next is a relation of displacement with initial and final velocity. Okay. Next we are going to see the fourth equations of the motion. What is the fourth equation? It's very simple. We are going to relate displacement with initial and final velocity. So we know that s equal to ut plus of at square. This is the second equation of the motion. We know that first equations of the motion, v is equal to u plus at. Then this equation is going to rearrange it as at is equal to v minus u. That at value going to taken as a v minus u in our equation. That is s is equal to ut plus of at into t. Instead of at we are going to substitute v minus u. That's why s is equal to ut plus of into v minus u into t. Anyhow, we are going to taken 1 by 2 inside of that equation and as well as the t also. S is equal to ut plus, we taken in 1 by 2 vt minus 1 by 2 ut. So here ut alone, that's why 2 by 2 if you substitute, there we have a 2 times is a 1 time. That's why S is equal to of Vt plus 1 by 2 Ut of 2 minus 1. The 2 minus 1 is nothing but a 1. That's why S is equal to of Vt plus of U into T. Commonly, of and T are taken out. S is equal to of that is V plus U into T. That's why we can take on V plus U divided by 2 into T, that is called as a relation of the velocity with the displacement. So for we have 4 equations of the motion, that is called as a kinematic equation. Kinematics equations for motion under that constant acceleration. That is, the first equation is V is equal to U plus AT. Second one is S is equal to UT plus of AT square. Third one is for V squared is equal to U squared plus 2AS. Fourth equation is S is equal to U plus V divided by 2 into T. U plus V divided by 2 into T. These 4 equations for the motions should be constant acceleration. Any object moves in a straight line with a constant rate of change of velocity, then only that acceleration is a constant acceleration. Where we have a constant acceleration, there only we can use this equation. Apart from that, we cannot use these equations. Example, if any particle moves in a uniform circular motion, if a particle moves in a uniform circular motion means magnitude of velocity changes with respect to time uniformly, but direction also changes. So that's why here, for in a uniform circular motion, there we have a centripetal acceleration only, not a linear acceleration. Where we have a linear acceleration, there only we can use. So that's why these equations cannot use in a circular motion and rotatory motion. In a straight line motion only we can use these equations. But we have derived this equation by using a calculus. Then these equations of the motion going to applied for some practical applications. So what are the practical applications we have? The particle which are moves in a straight line without changing the direction, that may be taken as a practical applications. Simply we can take on, if you take on any one of that chalk piece, small piece of chalk piece you are going to take on, if you leave, what it can be did that move towards that ground surface because of gravity. So that's why if any particle, if you make a free fall, that can be moves in a straight line towards the ground with a constant acceleration. That acceleration is happened only by the gravity. near that ground surface, close to that ground surface of the earth, acceleration of that all particles remains constant without air resistance. There is a Galileo's concept. When you have for a free fall object, acceleration remains constant. That acceleration may be taken as a g acceleration due to gravity. If you take any object, if you throw upwards, vertically thrown up object, if any object moves vertically thrown up the upward directions, they are also under a gravity only it can be moves. So that's why that also moves in a constant acceleration. There we have a positive acceleration as well as the negative acceleration. Positive acceleration is taken as a increase in velocity with respect to time. Negative acceleration is a decrease in velocity with respect to time. So anyhow, we are going to apply these 4 equations for some practical applications. That is going to take an equation of the motion under a gravity. Okay. Equations of the motion under a gravity. Under a gravity, particle can be moved downward or upward direction, but in a particular line. Anyway, there we have 2 ideas. An object falling from certain height h. You are going to stand on that your building from a terrace. If you leave one of that object, stone, if you leave the object, that will directly move towards that ground surface, moves only in a gravity, under a gravity. Otherwise, if you throw any particle with some initial velocity downward direction, there are also motion under a gravity also. Now we are going to see the most important one, that is free fall object we can consider, but we are throwing with some initial velocity. For that we can take on some diagram. We are going to stand on that our building. The building height may be taken as a h. From there we are vertically downward we are throwing object. If you leave the object in a downward direction, the force of gravity may be act on it. So that's why the particle is accelerated by the gravity. So for deriving the equations for downward direction falling, we are taken that coordinate axis, x and y axis. For our convenient, we will mention downward positive y axis is the x axis. For our convenient, we are representing, because generally xy axis can be taken like that alone. For our particle movement is downward direction, that's why that the positive y axis is taken in downward direction itself. Positive y axis means that the direction is represented as j cap. Positive x axis I cap anyhow. So here the particle is moves along the y direction only. So that's why the gravity is acting in y direction alone. That's why acceleration is in only y direction. Other than that y directions, x and z directions, no acceleration. That's why we can take an acceleration along the x direction is 0. Acceleration along the z direction is 0. We have the acceleration in y direction, y. Because of the gravity, we can take an g and notate that j cap. Then in our equations, we have the 4 equations. First equation is v is equal to u plus a2. If you throw with some initial velocity, there we have a u value. But acceleration is only by the gravity. That's why here this equation is changed as v is equal to u plus gt. Instead of a, we can substitute gt because moves under a gravity downward directions. Second equation we have. What is the second equation means? S is equal to ut plus half at square. If you throw the object downward direction with some initial velocity, after the leaving the object from our hand, there are gravity only acting. That's why instead of a, we can take an g. So it is moving in y directions. It will cover certain distance. That's why the displacement taken as s is equal to y. And the time can be taken as a t. So if you substitute, we will get y is equal to ut plus half gt square. The second equation for downward, falling downward object, first equation is this. Next we are going to tackle that third equation. Generally we have the third equation, v square is equal to u square plus 2as. We know that acceleration is due to the gravity. Displacement is taken as s is equal to y. If you substitute, we will get v square is equal to u square plus 2 instead of a, g, instead of s, y. Then fourth equation we have. That is s is equal to u plus v divided by 2 into t. Now we can take an, instead of s, we can take an y. Y is equal to u plus v divided by 2 into t. So the four equations for falling the object downward direction under a gravity. First equation is v is equal to u plus gt. Second equation is y is equal to ut plus half gt square. Third equation is v square is equal to u square plus 2gy. Fourth equation is y is equal to u plus v divided by 2 into t. If you throw downward direction with the initial velocity, means these four equations. If you leave an object from your hand, the motion starts from your wrist. If you leave a chalk piece from your hand from a certain height, that initial velocity is 0. Starts from wrist. Rest means u is equal to 0. What about these four equations? Here v is equal to u plus gt, u value is 0. That's why v is equal to gt itself. Then second equation, y is equal to ut plus half gt square. The u value is 0. That's why y is equal to half gt square. Third equation, there also initial velocity is 0. That's why v square is equal to 2gy. Then fourth equation, y is equal to vt divided by 2. If it is a free fall object, the equation, four equations can be changed as v is equal to gt, y is equal to half gt square, v square is equal to 2gy, and y is equal to vt by 2. Anyhow, these are the free fall object. Which one is called as a free fall object means object live from certain height which are closer to that ground surface. That height can be taken as very small as compared to the radius of the earth. The acceleration remains constant without air resistance. Then that particle makes a free fall. That is called as a free fall object. Our height should be very small as compared to the radius of the earth. If you make a leave an object such height that height is too small as compared to the r, then we can say that the object makes a free fall of this alone. Okay, next is equation second And third equation I am going to tackle. What we are going to tackle means, we are leaving an object from a height and reaches the ground surface. So their displacement is height of the building. Height of the building is the displacement. Time to reach the ground, final time, total time. That time can be taken as a capital T. So that's why y is equal to h, small t is equal to capital T. If you substitute this in our second equation, we will get that h is equal to half g capital T square. Then time to reach the ground surface can be taken as t square, that is h is equal to half gt square. Here I want to find that t is equal to what we can take means, that is 2h divided by g make a square root. Time to reach that ground. Time to reach the ground, t is equal to square root of 2h by g. Same time we are going to find that final velocity of the object to reach the ground. For that we are going to tackle this equation. That is v squared is equal to 2g h. That is the final velocity means that is a v ground square equal to 2g h. So we need that v only. That's why v ground equal to square root of 2gh. So final velocity to reach the ground depends upon that height only. That g remains constant. Like that, time to reach the ground depends upon that height. That is, time to reach the ground proportional to square root of height, and the final velocity, ground reached velocity also proportional to square root of that height. This is the most important equations for reaching the ground. Okay. Next we are going to see that object thrown vertically upwards. There also we are applying these equations of the motions. There we have here 4 equations, that is v is equal to u plus at. Second equation, s is equal to ut plus half at square. Third equation, v square is equal to u square plus 2as. Then we can take s is equal to u plus v divided by 2 into t. Here we are going to throw an object in upward direction. So for that we will take a diagram. Is the ground surface. From the ground we are standing on the ground and throwing the object. It may be moves in an upward direction. But what happens means the particle is moves opposite to the direction of the gravity. That's why if it moves in upward, their velocity decreases. So that's why here axis we can take is the x-axis, is a y-axis for our convenient. If you thrown with a certain initial velocity u, it may be moves upwards and final velocity may be 0. So anyhow, between we have certain velocity, but at the maximum height, final velocity becomes 0. So this concept, the time, initial time t is equal to 0, that can be taken as a small t, or sometimes it can be taken as a capital T. For that, if you substitute in between this movement, suppose if you take on this point, we have a certain final velocity. There equations, first equation can be taken as v is equal to u. Opposite to that, gravity can be moves. Gravity is acting in downward direction. G is acting downward direction. That's why v is equal to u minus gt for vertically upward thrown object. First equation. Second equation is s is equal to ut plus half at square. There the gravity is downward direction, movement is upward direction. That's why we can take on, if it is a y-axis, y is equal to ut minus half gt square. Then third equation we have, there between that movement we have a final velocity. That's why v square is equal to u square minus 2gy. If it is reaches the maximum height, final velocity becomes 0. Anyway, fourth equation is, we can take y is equal to u plus v divided by 2 into t. at the maximum height. Final velocity is 0. S is equal to h. So if we substitute it, we will take on first equation is 0 is equal to u minus gt. From that, u is equal to gt for maximum height. Okay. Second equation we have at the maximum, we will get that displacement is h. h is equal to ut minus half gt square. Then third equation, final velocity is 0. That's why 0 squared is equal to u squared minus 2gh. That's why u squared is equal to 2gh. Then u is equal to square root of 2gh. Then fourth equation, the final velocity is 0 means y is equal to ut by 2. These are that equations for vertically thrown up object at the maximum height. Anyhow, we have here 4 kinematic equations. Very simple, we can recollect that. First equation is v is equal to u plus at. Second equation is s is equal to ut plus half at square. Then third equation is v squared is equal to u squared plus 2as. Then fourth equation is s is equal to u plus v divided by 2 into t. Thank you for all to go through your book itself. Any doubt you have, you contact me and we will discuss it.